Okay, so if you recall, in my last class, what I did your line integrals of your vector functions. Line integrals of vector functions. Okay, and over here, what we did, we were defining it as. I just don't want to go back to definition. We denoted it as this. Okay, so what it is, I mean, here f is a vector value function, f is a vector value function, or f defines a vector field, okay, which is, I mean, continuous in a domain D. So basically that means that the components of f, they are, I mean, functions of, suppose if I define f in space, functions of x, y, j. So if all those three components, they are continuous, I mean, in some domain D, and if C is a curve lying in that domain D, so then the line integral of the, I mean, vector function f is denoted by this, and this can be interpreted as the work done by the force F in moving a particle along the curve C, or moving some object along the curve C. Okay, and we have seen that this can be, we can write this further as your okay, or this can, and of course here we are going to write it as A, B, and this can also be written as F, T, ds. Let me explain it to you again. Although in my last class I have already done this. So basically what it is, if, I mean, the curve C can be parameterized by the parameter T, which lies between A and B, and the curve C can be defined by the vector, say RT. So then this can be written as this, and this is nothing but what happens when your this T is a unit vector, on the curve C at a particular point. Okay, and this I have already explained what ds means. Okay, all this stuff. So let us try to work out one particular example. Say, suppose you have to evaluate this. Where your f is given by xyi plus yz j plus jxk, and C is the curve given by the twisted cubic. It is x equal to t, y equal to t squared, j equal to t cube, and your t lies between 0 and 1. Suppose, so basically the question is about evaluating this line integral where f is given by this, okay, and C is nothing but the twisted curve whose parameterization is given by this. That's it. Okay. So if you recall, so what I'm going to do. So, and again, let me tell you another thing. This one. Say, suppose f is something like your f1, f2, f3. So if your r is given by this vector, this xyj, so then your f dot dr, this is simply going to be f1 dx plus f2 dy plus your f3 dz. So if you wish, what you can do, we can write this in this form also. C f1 dx plus f2 dy plus f3 dz. And what happened earlier, that we already did what? I mean, line integrate with respect to x and y. So we can do line integrate with respect to z also, right? So here, then what you have to do, now we are going to convert it into convert it as a function of t. So then what is going to happen? Your f1 is simply xy, right? And what is the parameterization here? So xy is going to be your t cube. Is it okay with everybody? Fine. Xy is going to be
Yes.
t. And dx, if you consider x equal to t, dx is simply dt. Okay? And then yz is going to be t square into t cube, that is t to the power 5. And dy is going to be 2t dt. And then your zx is going to be t cube into 2. This is t to the power 4. And dz is going to be your 3t square dt. Okay? And since your t lies between 0 and 1, so the lower limit is 0, upper limit is 1. Okay? So now simply you have to perform. So here t to the power 5, and this is going to be t to the power 6, right? So 2t to the power 6 and 3t to the power 6. So 5t to the power 6 plus t cube 0 1 dt. So simply integrate it. Whatever value you get, you will get the final result. So basically, again, let me reiterate that what is important here is like the parameterization part. I mean, here C is explicitly given, so that is why I mean walking this out was pretty straightforward. But sometimes C may not be given explicitly. You may be given an informal description of the curve C, and then you will find out C yourself. Okay. Okay. Fine. So now let us move to. And of course, we are going to do a lot of other exercises. I mean, you will find them in your tutorials. So let us come to a very important concept: fundamental theorem of line integrals. Fundamental theorem of line integrals. Okay. So now, firstly, let me try to bring one analogy of this fundamental theorem of line integrals with your fundamental theorem of integral calculus for a function of one variable. Okay. So now, I mean, if say suppose I have to integrate a function, between a and b. So basically, I am considering a function in the interval a, right? And if the function is such that, I mean, it is the derivative of some known function. Capital F. So then what happens? This is simply f of b minus f of a. Right? This what constitutes fundamental theorem of integral calculus. Okay. So now let us consider, say, maybe what you can do. I mean, if you consider, say, 2D, I mean, we may define, I mean, a curve C. We may define a curve C whose initial point is A and terminal point is, say, B. Okay, and let the coordinates of A be your x1, y1, and let the coordinates of B be x2, y2. Similarly, I can consider the, I mean, same curve. I can not consider the same curve. I can consider the curve C, I mean, in 3D as well. in 3D as well. Again, in that case, if I have the initial point A, whose coordinates are x1, y1, z1, and terminal point is B, whose coordinates are your x2, y2, z2. So then it is going to look something like this. Is it okay? Fine. And let this be C, let this be C. So now, what is the fundamental theorem of integral calculus? What is the fundamental theorem of integral calculus? Here, if you consider C to be, it is a smooth curve. Huh? It is a smooth curve. It is a smooth curve. Okay, and this could be a plan curve, or this could be a space curve. Okay, and suppose it is given by its parametric representation. RT. You already know what it is. Okay, and where your T lies between A to B. Okay, fine. So now let F this be your differentiable function. Let this be a differentiable function, either in two or three variables. Okay, with the fact that its gradient vector grade F. Remember, this now I have wrote in the concept of gradient vector. So you know that the gradient vector, again, this is going to be a what? This is going to define a vector field. Okay, and if I assume that this is gradient function, this gradient function, or this gradient vector, if we assume that this is continuous along C, so that means at each point along the curve C, what is going to happen? The components of the gradient vector, they are going to be continuous. So you know what is this gradient vector? This is simply del f del xi plus del f del yj. If it is in 2D, it is going to be like this, and if it is in 3D, it is going to be simply this. Okay. So then what happens? The statement of the theorem is if you take the line integral of the gradient function along the curve C. So this is simply your it is simply given by this. So this basically is the statement of fundamental theorem of line integrals. Okay. So what does it tell you? If if you consider a function f which is differentiable, okay, and if you take the line integral, of the gradient of f along the curve C, then this happens. So basically, what does it mean? That eventually, if you evaluate this integral, it simply reduces to the difference between the value of the function at the terminal and at the initial, right? So basically, this becomes x2, y2, z2 if you consider it in 3D. That's it. Okay. So let us try to prove it. And you will see that it's very straightforward. Okay. So okay. So if we dr. So this, now if you recall the definition of line integral, this can be put in this form. This is the vector function and this I can simply dt, right? And t going from A to B. Is it okay? Fine. Okay. And you know that. I mean, this RP is what? Simply this vector xt, yt, zt. Okay. So then this is going to be A to B, and grade f is nothing but this vector del f del x, comma del f del y, comma del f del z, and then this dot, and so r prime t from here it is simply what? Dx dt, comma dy dt, comma dz dt, right? And if you take dot product of these two, so this is going to give you A to B. So this is going to be del f del x dx dt plus del f del y dy dt plus del f del z dz dt. Okay, this. So now remember. Just let me. Just say, suppose you consider a function, say phi, which is a function of xyz, which is a function of xyz. Okay, and each of x, y, z themselves are functions of the single variable t. So then, by same rule, simply what d phi dt is simply del phi del x dx dt plus del phi del y dy dt plus del phi del z dz dt, isn't it? Fine. Now, what I want to emphasize here is that because phi is a function of your xt, yt, zt. So if I consider this xt, yt, zt, definitely I'm going to evaluate phi at the point x, y, and z, right? At that point, if you draw a vector from the origin to that particular point, that is going to give you the vector rt, isn't it? So this is simply what? This is simply what? This is a function of, in fact, I could have written as this also. Is it okay?
Yeah.
Fine. So that is why this part, what I can do, this part, what I can do. So this is simply what? This is simply A to B, your df dt, this. Fine. Or I can simply write this as, your A to B. So it is the total differential df, right? So I can simply write it as you can have written it as f prime t dt also. I could have written it as f prime t dt. But again, in fact, this I could have written as, because f was first a function of x, y, z. Each of those x, y, z are a function of t. So this is simply going to give you, right? And t goes from A to B. So once you decompose it, not really decompose, once you plug in the values, so it is simply going to give you RB minus F R A. Okay? So now this brings me to one interesting observation. This brings me to one interesting observation. Okay. So what does it tell you? What does it tell you? That if you perform line integration of a vector which is the gradient of a scalar function, so then the value of the integral, it simply depends upon, I will say, I'm doing it along a curve C, right? But eventually what happens? The value of this integral, it simply depends upon the value of the scalar function at the initial point and at the terminal point. Is it okay? Fine?
Yes.
But remember, this is not for any function. This is not for any function if I take f dot dr. Okay, it is not for any function. If the function capital F, it is the gradient of some scalar function, only then this happens. So basically what is happening here? So if I join the initial and terminal point through some different paths, I am still going to end up with the same value, isn't it? For functions like this. Is it okay?
Yes.
Fine. So this is what fundamental theorem for line integral. Okay. So this is what is going to bring me to the concept of independence of paths. Okay, fine. So, okay. Should I repeat the concept of independence of paths right now, or okay? Maybe before that, let me define conservative vector field. And after that, I'm going to go to independence of paths. In fact, you have already learned a little bit about that. Okay, conservative vector field. Okay, say suppose I'm considering a vector field like say this XYZ in some domain D in say RQ. Okay, fine. So then, if this vector f can be expressed as the gradient of a scalar function phi, say, gradient of a scalar function phi, then we say that f is a conservative vector field. Okay, and this phi, it is called the potential function. Is it okay? Fine. So that means here I have seen that since this function, it is the gradient of some scalar function. So that means I mean here the function, if I call this as f bar, so this defines a conservative vector field. Is it okay? Fine. Now let me come to the concept of independence of the paths. Independence of paths. So now you have seen that for vector fields like this, okay, what happened here? I mean, whatever path you are going to take, if you perform this integration, grade f dr, C is a curve joining the points A and B, and if C1, C2, they are other curve joining the same points A and B, because the value of the integral depends only upon the value of the functions at the initial and terminal points, so that this value, it is going to remain the same, isn't it? So in that case, we say that the integral is independent of the paths joining the points A and B. Okay, but you shouldn't be under the impression that every vector field, if you consider the line integral of that vector field along a curve, then we can get independence of the paths. So let me give you an example. Can I get an example which you have already done? So let me consider this example. C y squared dx plus x dy. Okay, so that means here this is simply C your f dr, where f is given by the two-dimensional vector this. Okay, and r is simply your xi plus yz. Is it okay? Fine. This problem we have done, but what we did, if you recall, what we did. So I think I took the point -5, -3, and your 0, 2. This one, 0, 2. Okay. So what I did initially, I took the straight line part, this, and then what I did. Okay, so initially, say, suppose this is A, this is say B. Okay, so what I had taken initially, I had taken, my C to be C1, where C1 is nothing but the straight line joining A and B, and then I had taken C to be C2, where C2 is x equal to 4 minus y squared. Okay. C2 is nothing but the parabolic part given by x equal to 4 minus y squared. Then we have seen that, if I evaluate this integral along your C1 and C2, they give you two different values. Is it okay? You definitely remember it, right? In my last class I did it.
Yes, yes.
Right?
Yes, sir.
So that means this integral is not independent of the paths joining 2 points A and B. Okay, fine. So now what is the independence of paths? Say suppose I consider this integral, okay, and suppose I consider it along the curve C1, where C1 is a curve joining the points A and B. If C2 is another curve joining the points A and B, and if this happens, for that matter, it happens for any curve joining the points A and B, then we say that this integral is independent of the paths joining the points A and B. That's it. Is it okay? Fine. So now let me just run through my slides a bit. So this is what it is. So this was the example that we had taken. Okay. So this was, let's say, example 4, and we know that from example 4, that in general, this does not happen. Your C1 f dot dr is not equal to C2 f dot dr. Okay. But one implication of theorem 2. Theorem 2 is nothing but the fundamental theorem of line integrals. Okay. So it says that this grade f dot dr, if you take this integral along any path joining 2 points, then they become equal. Okay. So in other words, the line integral of a conservative vector field depends only on the initial point and the terminal point of a curve, because I have already defined a conservative vector field. It is nothing but if you can express a vector field as the potential of not necessarily potential as the gradient of a scalar function, right? Gradient of a potential function. That's it. Okay. So in general, if f is continuous, f is a continuous vector field with domain D, we say that the line integral, this one, f dot dr along the curve C, is independent of paths if this happens for any two paths C1 and C2 in D, and we have the same that D that have the same initial and terminal points. Okay. So with this terminology, we can say that the line integrals of the conservative vector fields are independent of paths. Okay. So now the next thing is going to be very interesting. So now the question is, like say here, I mean here I was considering this function, okay, and we saw that integral was not independent of the paths. I mean, joining any 2 points, not necessarily any 2 points, joining these 2 particular points in some domain. Okay, so now the question is, how can we identify a function f to be conservative or not? Okay, whether this constitutes a conservative vector field or not. Okay, so basically, I should be able to, if say f is a, I mean, let us start with 2b, right? So I must be able to find a scalar function phi such that your f1 equal to del phi del x and f2 equal to del phi del y. Okay, so now let us see when does that happen. Okay, so for that we have to again like understand some more concepts. Let us just quickly go through those concepts and the slides, and after that I'm going to come to those theorems, which is going to give you an answer to that question that I posed. Okay. Now let us come to your closed, open, connected, and this simply connected. Maybe I don't know whether I'll be able to finish in this class itself, but let us see how far we can go. So let us come to your, I mean, closed curve. Let us come to the concept of closed curve. And this open, it is not about a curve. Remember, this open is about a region D. Okay, fine. So let us concentrate on the closed curve for the time being, and after that I'll come back to this open. Fine. Okay. It can be in space or it can be in plane. Okay, so let us start with a planar closed curve. So what is that? I mean, you know, like say this is a closed curve. This is a closed curve, isn't it? This is a closed curve. Okay, this is a closed curve. So what makes it a closed curve? Say if you start at any point, if you start at any point, then what happens? Again, you end up with the same point. Is it okay? Fine?
Yes.
Right? So that means the initial and the terminal points, they are the same. Okay? So that means, what is the meaning of this? Say, suppose this RT is the parameterization of this curve. Okay? Where T is defined in this interval. T is defined in this interval. Okay? So that means we start with T equal to A and we end up at T equal to B. Right? So that means what happens here? R at A is equal to is it okay? Fine?
Yes.
This is what happens. Okay? Now, let us see the independence of the path concept. Just give me a sec. This is about, okay? Okay. Now, suppose I consider this line integral along the curve C, okay, in some domain D, okay, and suppose I have been given that this integral is independent of that. So that means we must have I mean one initial point and one terminal point in such a way that what happens I mean yeah, so if you evaluate these integrals along different curve joining those 2 points, you arrive at the same level. Is it okay? Fine. Yes. Let us now. Let me do like this so that I mean, yeah. Say suppose I have something like this. This is C1. This is C2. This is C3. Okay. Fine. Okay. Now, say
Yes.
I have simply been given that C is a curve. C is a curve, and this line integral is independent of any path line in that region D. Okay. So what happens? If C is a closed curve? C is a closed curve. Right? So then, what is going to happen? Now, C is a closed curve. I know that C can be obtained by choosing the same initial and terminal points, right? But what we can do, I can simply consider two different points, 2 points A and B lying on the curve C, which is different from each other. Is it okay? Fine. So overall, this curve is C. So now, suppose the path from here to here, this is C1. Okay. Let me suppose this blue curve is C1. Okay, and the yellow curve. Okay, maintaining the same orientation. So suppose this is C2. Fine. So far so good. So then I have been given that this is independent of the path. I have been given that. Okay, fine. So now you know that your the C is simply, and again this curve, I mean C, this closed curve C, it can be some piecewise what? Piecewise smooth curve. Okay. So we have already seen that I can write this as f dot dr plus C2 f dot dr. Is it okay?
Yeah.
Fine. So now, see, the orientation of C2 is this. If I consider, I mean, this C2, see here this C2 is a curve from B to A, right? But if I want to consider the curve along the path in the yellow line from A to B, so in this direction, it is simply going to be minus C2. Minus C2 is going to be this direction. Is it okay? Fine. So that means what I can do, I can write this as C1 f dot dr. Okay. So if I want to write this in terms of minus C2 f dot dr, so this must be minus. Is it okay? Yes?
Yes.
Right? Now, what was given to me? What was given to me earlier? I was given that this integral is independent of any part lying on that region D. Yes? So what does that mean?
That is 0.
That is 0. That is 0. That is 0. Because you take, see, remember, the original C as a closed curve, we had taken the initial and terminal point as the same. Right? So now what we have arrived at, like we have arrived at two curves having the same initial and terminal points. Okay. So now, because we have the property that integral is independent of any path joining any two points, so that means this integral must be equal to this integral. So that is why the value of this is equal to 0. So that means if that property holds for a closed curve, if the property of independence of path is there, so along a closed curve, you should always get the value of that line integral to be equal to 0. Okay, fine. And again, the converse also you can prove. What I want. So converse, you prove it yourself. So this is going to lead me to one theorem. That is what I am more interested in. Okay. So that I would like to show you. I'll come to that open reason later on. That theorem is here. I think I have forgotten to. No, I think I have write down the theorem. Okay, so this theorem is simple. Just a minute. This theorem it is very straightforward. Sorry. lying in D, your containing the of C. So if and only if and only if. Okay. So I have done the if part, the only if part, you do yourself. Okay. So now what?
That the board cannot be seen.
Yeah, I'm coming back to that. Yes. So yes. So this is the thing. If this line integral is independent of any part lying in D which contains the curve C, if and only if this happens. If and only if this happens. So I mean we have already proved that if this is independent of the part, then this happens. Now we have to prove that if this happens, okay. So then I mean, for any two curves C1 and C2, you are going to get this along C1 to be equal to this along C2. Okay, fine. So now let me come to the concept of your open region. Open region. Okay, so what is an open region? So if you consider a region D, say, if you consider a region D, so if D is such that what if you take any point, say, let me consider this to be a region in R2. If you consider any point, I mean xy belonging to D, then every disk having xy as the center, every disk having xy as the center, it again entirely lies inside D. Okay, so then we say that D is an open region. Okay, so and now again this was about open, and D is said to be connected if if you take any 2 points, lying in D, so then the any curve joining those 2 points again lies in D. Then D is said to be connected as well. Okay. They are doing.
Sir.
Yes, yeah, you please go ahead.
Not any disk of arbitrary radius.
That is what I said. That disk, when see you take any point lying in D, right? And you consider any
no, there exists.
Yeah. Sorry, not any disk. There exists at least, right? There exists at least one disk. Sorry. Sorry. There exists at least, because I mean, if you take a disk with big radius, it may go outside that reason. Sorry about that. So if you can find a disk with center, that particular point with center is nothing but, see, let me come back to that definition again. Sorry. You say for each point lying in D, I can always get a disk, say D epsilon, centered at xy, which entirely lies inside. I think I told about every disk, right? That was wrong.
Yes.
Yeah, I do, because if I consider every disk, I can consider a disk like this also. Isn't it? Right? So finding one such disk is sufficient. Okay, for D to be open. Okay, and in addition, again, D is said to be connected if any 2 points in D can be joined by a path that lies again entirely in D. Okay, so this is going to be important in our next theorem. So the next theorem is, again, I told you that what guarantees you that if you consider a vector function, that function is going to define a conservative vector field. Okay. Yeah. So let us show you some theorems here. Okay. So what I'm going to do, I'm going to do theorem 4, and this theorem 5, you will see that it is going to be pretty straightforward, kind of direct consequence. It is going to be pretty straightforward. Okay, so let's try to do this. Well, what is it is saying? So suppose F is a vector field that is continuous on an open connected region D. So that is why I had to broach up the definition of an open and connected region because this is an integral part of this theorem. So, and if this f dot dr, this line integral is independent of parts in D, then F is a conservative vector field in D. Okay, so for guaranteeing F to be conservative vector field, so that means I should be able to express F as the gradient of a scalar function if this is independent. If this is independent. Okay, so what we are going to do, I am going to assume that this line integral is independent, and from there I will prove that I can always construct F to be something like this. Okay, fine. Just give me 10 seconds. Let me. Okay, so what I am going to do here, you consider a fixed point AB, which lies in say D. Okay, and then what I am doing, I define this function, which is a scalar function. I define it to be your AB to xy, AB to xy, and then f dot dr. Then f dot dr. Okay. So now what I have done, if you look at this, what I have done here, I have simply defined a fixed point AB and a variable point xy, right? But I still haven't told you how the paths joining the points AB and xy, how this path is going to be. Is it okay? Fine. Okay. And again, let us remember the fact that what is the assumption is that if you consider this integral where C is any curve lying in the region D, and this is what I have been given that this is independent of the paths joining the initial and the terminal points. Is it okay? So this is what we have. Fine? Okay. So now, say, suppose this is your D. Suppose this is your D. What I'm going to do firstly, say, suppose this is your point AB, which entirely lies inside D. And now my point, suppose this is XY. I'm going to change something, so that is why. So what I'm going to do, I'm going to consider the curve C to be something like this. This is a horizontal line. This is a horizontal line. So I am considering my C to be consisting of the curve C1 and this C2, okay, where C2 is nothing but the horizontal line segment joining the point x1, y and xy. Is it okay?
Yeah.
Yes, sir.
What is
Yeah.
X1?
X1, y. X1 is your less than say x.
Okay.
X1 is less than x. I have chosen it in that way. Okay, it can be less than equal to x also, but I can keep it like this so that I mean I don't end up with the same point. Okay, and now you may be asking how this is possible, because the D being open is going to guarantee me this. Because what I can do, say suppose because this xy it lies inside D and D is an open set, right? So D is an open region to be precise here. So then I can always find a disk, right, centered at xy, which is going to entirely lie in D. Okay, so what I'm going to do, I'm going to choose this point x1, y to lie inside that small disk. Is it okay?
Yeah.
Fine. So that is what I'm going to do. Okay, fine. So this is always possible. This is always possible. Okay. So then what is going to happen? Then you say f of xy. So this is because as I have told you, say this is my integrand. Integrand is simply it is a line integral, right, along a curve joining the points a, b to xy. That's it. Okay. So that is why f of xy is simply this. Okay. Fine. And this I can write it as simply your C1 f dot dr plus C2 f dot df. Is it okay?
Yeah.
Yes, sir.
Fine.
Yes, sir.
Okay. So now yeah. So now let us assume that your this f, this is say pxi plus u xi. Okay, fine. And of course your r is simply xi plus y. Fine. So then this is simply going to give me. I may say this C1. So this is PBX plus q dy, and this is c2 p dx plus q dy. Sorry. Okay, for the timing it is fine, right? Okay. So now you look at one thing. What is happening? What is happening along C2? What is happening along C2? Here y is fixed, isn't it?
Yeah.
So that is why your dy it is going to become 0. Is it okay?
Yes, sir.
Yes.
That is why. That is why. So I can write it like this: pdx. Okay, and so that means your C2 it is from x1 y xy, right? I can write it like this. Okay, fine. I'll deal with that later on. So now let me come to this one. Let me come to simply C1. Okay. So now again your C1 AB x1y. Is it okay? C1 is simply AB x1y.
Yes, sir.
Okay. Yeah. So now see, just a minute. Even if I don't break it up, if I simply okay, let it be like this. You don't need to worry about it. Now, what is happening out here? What is happening out here? Eventually, okay. See, once you perform integration here, what you are going to get? You are going to get, I mean, it as some say function of xy, right? Is it okay? And the limit of those, they are going to go from AB to your x1 y. Is it okay? I'm talking about this integral. I'm talking about this integral, the first integral, right? You are going to end up with as if you integrate it as a function of x and y, and then because my initial and terminal points are your AB and x1 comma y, you are going to end up with something like this, right? And you will see because A, B, and x1 they are fixed. Yes?
Yes.
Isn't it? So that is why eventually this one after integration it will turn out to be a function of y only. Is it okay?
Yeah.
So that is why if I try to find out partial derivative of small f with respect to x, then from this expression, in fact, I don't even need to write it down, but anyway, fine. So this expression, it is going to give me 0, right? Plus del del x. Now look at that one. Del del x. Look at that one. So this is what I can do. This I can write as p your x1 is fixed. I can write it something like this, right? Yeah. Is it okay? Check whether I'm fine or not.
The y variable is fixed.
Why? I think I did the wrong way. No. No, sorry. This is not dt, sorry. I can rather I can write it as your y is fixed here. Sorry, y is fixed here. So that is why I can write it as simply y. Sorry. And x is varying. X is varying, so I can introduce a dummy variable line. I think now I am fine. Yes, I think now I am fine.
Yeah.
Okay. So, and if you differentiate it partially with respect to x, so this is simply going to give you p of xy. Okay. Are you getting the point? This is differentiation on the integration side.
Yeah.
Because this is see, whenever you do a partial differentiation, you keep y as constant. Here anyway, y is fixed, right? So then what happens? This is fixed. It is something like what? A to x. I mean it has become something like this, isn't it? Right? So that is going to give you simply p of x.
P of
right?
x.
Yeah. So the same thing is happening here. The same thing is happening here. So that means I have got del f del x to be equal to p of xy. So now next what I am going to do, I am going to do another approach like before. I am going to take, this approach now. See what you do, you take C1 to be the curve from your AB to XY1 and then C2 to be the vertical line from XY1 to XY where your Y1 is less than Y. You do the same approach. So then what is going to happen? You are going to come up with del f del y equal to Q of xy. Is it okay?
Yes,
Fine?
correct.
Right? So that means what we have found out, that if your this integral is independent of parts, then f equal to pi plus qj, this becomes del f del xi plus del f del y j, and this is simply nothing but del f. Okay, and that is the theorem. Okay, fine. So this is the, basically what? The necessary condition for a vector field to be conservative. Fine. So now what you see here, if the second order partial derivative of small f, it is continuous. So then what is going to happen? I must have del 2f del x del y. So this is going to be equal to del 2f del y del x. Okay,
Yeah, Clairaut's theorem.
Yeah, Taylor's theorem. So from there, what I'm going to get, since P is equal to del F del X, so del P del Y, this is going to be equal to del 2F del X del Y, and similarly, since your Q is equal to del of del Y, so what is going to happen? Del Q del X, this is again going to be del 2Y del Y del X, or I mean because they are equal. So eventually, since they are equal,
That will be del 2F.
or delta F, sorry. Yeah. So what is going to happen? I am going to get del P del Y equal to del Q del X. Okay. So that is going to be, if you look at this, so this is what happens. If fxy is pi plus qj is a conservative vector field, so then you already know if it is a conservative vector field, then f can be expressed as a, what? Gradient of a scalar function. So where p, q have continuous first order partial derivatives on domain D. So then throughout D we have this. Okay. So this is a consequence of this, but I still have to define simply connected. So in my next class, I'm going to go to your Green's theorem. Okay. So I'm going to go to Green's theorem, and hopefully we'll be able to finish our course. I mean, within another 5-6 classes. Okay. So till then, I'll meet you in my next class.